Hi guys, Shouvik here. Welcome back to YouTube channel. So today we will solve another question from Leetcode itself. So let's get started. Yes, so today we have these problems. Lexicographically smallest equivalent string. Yes, so on this problem statement, it has to act as a medium, and I feel so it's quite good problems in interview perspective. I would suggest, because on this particular problems you like little bit intuitions you have to think of, little bit optimizations you have to think of, and the very standard graph traversal algo you have to incorporate to solve it. So I personally like these problems. Like any product based company perspective, this is going to be a, like, in moderate difficulty, a very good organized problems altogether, I have to say. So now they have given two integers of same length, s1 and s2, and a string base string, right? So these things they have given to us. We say s1 and s2 are equivalent character. For example, if s1 of abc and s2 equals to cde, then we have a equals to c, b equals to d, and c equals to e. So these three conditions should satisfy these three conditions is bound to be going to happen. Equivalent characters follow the usual rules of any equivalence relations. So what is this? What is this? Reflexivity. So what is this reflexivity? If a should be equals to a. Symmetry. AB, if AB is equal, then you can say BA is also equal. Transitivity. If AB equals, BC equals, then transitively you can say AC is also equal. So this reflexivity, symmetry, and transitivity, these three principles should follow. Now, for example, given the equivalency informations from S1 ABC and S2 CDE, ACD and AAB are equivalent strings of base strings EED, and AAB is the lexicographic smallest equivalent strings of base strings. So this particular things I am not able to also understand. So I will not take this example to get you the gist. I will take exact sample test case to basically give you the gist. And finally, what we have to do, we have to return the lexicographically smallest equivalent string of base strings by using the equivalency informations from S1 and S2. So now let's go to the sample example test cases. So these lines you can skip. So there is, like, I feel there is some wrong like mappings they are using, but on sample test case mappings is correct. You will get the entire gist. So we have given two same length strings, one S1 and S2. So by this you can see this P and M is a single group. This A and O is also a single group. This R and R is a single group. This K and R is a single group. This E and I is a single group, and this R and S is a single group persons. So now with this equivalency, we can group their characters MP. So here you can see MP is a group. A and O is a group. Then we have, for R, we have mapping of whom? We have mapping of R only, right? So R is a single group right now. But for this K is also mapped to R. So R and K are both in a single group, right? And here E and I is a group. And this R is pointing to S. This R is pointing to S. So now if I can quickly go to our OneNote. So from R you are able to go to, from K you are able to go to R. Let me write it. So I am basically stating K is equivalent to R, and R is equivalent to whom? Tell me, guys. R is equivalent to, on the last go, this R is equivalent to S. So now this R is equivalent to S. I think I already wrote it correctly. So by transitivity, can I write K is equivalent to S? So I will just group it. Who are possibles to in a single group. K, S and R. These three can be a part of a single group. Agree, guys? Agree? Yes. So these three can be part of a single group by transitivity principles. So here you can see KRS is a single group. So the answer now if we try to use the equivalency, we have the equivalency mappings of every characters. Now for M, the characters in each groups are equivalent and sorted in lexicographically order. So this point you guys have to take a note. So if AO is a group, then AO is only going to be occurred, like only first is the smallest and O is going to be the largest one, but never OA. So now if I am going to convert the base strings to its equivalent lexicographically smallest versions, then M, do we have a mappings of M which is smaller than M? We have MP, but M is the smallest of that particular group. So M is not going to be, sorry. The base strings is P. So P is going to be, which particular group P belongs to? P belongs to MP. Who is the smallest of them? M. So P is going to be changed to M. A is a part of a group. Yes, this group, but A is already the smallest of them. So A is intake, like as it is. It is not going to be changed. It is not going to be changed. It's as it is. This R, whom part, this group. Whom smallest, K smallest. R map to K. S, same group part. Who smallest, K smallest. So this R and S both map to KK. This E, yes, I am itself the smallest of my group itself. R, K, R map to be K. So that is the output that we have going to generate. So you can try on your own for this example test case, or maybe I can iterate to the at least one more example test case. So for hello world, H and this W is going to be same pair. This E, O are same pair, and you can see this from this O you are able to jump to D. So same transitive dependency. So D, E, O are in same path. This L you are going to R. So LR is same path. L to L same, no change. This O and D we have already handled transitive dependency D, E, O, LR. So now hold H, who is smallest? H itself, H as it is. O, which group? This group. Smallest is whom? D. So O will going to convert to D, H, D. L, I am the smallest of my group itself. D, I am the smallest, D. So H, D, L, D. That is the output string. So you can try on your own for this example test cases also, and you will going to get for this base strings, you are going to get these strings as an output. So now on constant you can see like it is of in the range of n is in the range of 1000 odd. N is in the range of 1000 odd. And S1 length and S2 length both are same. And S1 and S2 and base strings consist of only lowercase English letter. So that's all about the problem statement, and I feel so I am able to explain it on very first go. The problems is I would suggest like is quite understandable also if you cover to read it till sample test case. But yeah, if it is not, then with the whiteboarding also we have understand how the things are actually work. So now let's try to build a super solid intuitions to solve it out. So what I am basically looking for. So I have characters from small a, b, c like this dot of small z, right? Small a to small z. So these characters we have at. Agree? Now can you guys tell me like, are there some groups? We have just saw, right? There are some groups. Maybe some A, P, Q, S is a part of a group, and there are let's suppose A, there are B, then R, then M is part of another group, and let's suppose there are N, then what can I write? K, L, then Z. These are let's suppose another group. So there are group. The characters are grouped based on the transitivity or whatever it is. So now how you are basically forming the group? So you are forming the group based on the principles. If for the first group, if I am going to write it, so maybe A and P, you are going to get a direct mapping. From A to P you are able to move, and from P to A you are able to move. But Q, how Q is going to be in picture? So maybe on some character for A, it can also map to Q, or it can be a one possible way, or this P can be a part of a Q. P is going to map to Q. So either of them. So let's suppose I am going to consider this only. So A, P, Q. So like this way, all the things are grouped. Then there is we have one more S. So S can be either part of this A, this P, or this Q, right? It can be a part of either of them. Maybe S is attached here, or maybe S is attached here, or maybe S is attached here, right? So S can be a part of any of them. Then also they are going to be on the same group. So are you guys, after writing these things, are able to see any data structure? I think you should be like, after solving like 80 plus days of problems, you should be identifying what actually the data structure is going to be set. Right. So I have just make a group, and now I have just unwrapped the groups in kind of a visualizations in a data structure. So if you can set some data structure to this particular algo now, particular problems of this particular, are you able to find any data structure from these visualizations? Are you able to find any data structure? Yes, man. Yes. That is for Shiora graph. Now initially what I have written. So this all things. So the groups is actually nothing but a subgraphs, and this is another subgraph. This is another subgraph. So it is part of a different graphs altogether. So these are actually disconnected, not connected. That is the beauty. So this is are actually disconnected graphs, disconnected small subgraphs. It's forming subgraphs. It's forming. Agree, guys? Agree? Definitely. Now if you just try to build the adjacency list representations of this graph, then the things is going to be like a very cakewalk for you. So now if I am going to make a graph for the first one that we have already made, no, A, P, then from P, let's suppose this Q, and let's suppose from this P we have this S. So now we definitely need a mappings, right? So if someone is basically looking for, or maybe in our base strings, if we are going to find any occurrence of P, then which characters we have to map? Who is the smallest of this subgraph? We have to smallest one, that is nothing but A is in our case. If there is a query of Q, if our characters of in the base strings is Q, whom we have to map it? Who is the smallest? A is the smallest. So for S, whom we have to map? A. If we going to encounter A, I am the smallest. So like this way, for every subgraph, so every small subgraph, we want to know, we basically we can trigger a DFS or BFS, whatever you are comfortable with. You can trigger a DFS or BFS. Anything is going to be work. You just need to create the mappings. You just need to create a mappings. What we basically looking for? We need these mappings, no? So when there is a map, when anyone asks for P, we should have this P to A mappings is already stored in some our DP or whatever the tables we are for basically maintaining. So we need the mappings initially present when we are basically playing the game with our base strings, right? So in base strings, we just want to know who is the smallest of this particular component, which particular components it's belonging to, and who is the smallest of them. So if we can statically store previously of base strings iterations, if we can store it to some to kind of a mapping things, like P is going to be mapped to 1 A, Q also mapped to A, and S also mapped to A. So if we can able to store it, and obviously A should map to A. So these mappings we need it. We definitely need it. So what we actually need, we can trigger either BFS or DFS, and we can populate the smallest one. We can populate or fan out the smallest node to all of it means. So let's suppose you are going to start with A, P, Q, and we have S, right? So this is the graph. So I am basically stating you that you can start your DFS or BFS from A, and our current value, which value we are basically want to propagate. So the value that you want to propagate, the smallest one to all of its node, is nothing but A only. So what I am basically asking you, when you are basically doing the DFS, the smallest value you can propagate to all of its nodes. So when you are basically, you don't need to actually override the value of P in the graph itself. So I am basically asking you should have, let's suppose DP of A, the mappings where you are basically storing, DP of A should hold A, DP of P should hold A, right? Because that is the smallest of this particular component. DP of your S should hold A, DP of your Q should hold A, right? So these things you have to populate. So you can start your DFS to any point. You can start your DFS to any point, right? You can start your DFS to any point, and you can try to populate or propagate. You can try to propagate or fan out the smallest value to entire graph. Not you don't need to override the value of the itself graph. You can store the mappings to your DP. Because I know for this particular graph, that is the smallest I need to store in our DP for all the nodes the graph have had. Now you will definitely ask me a question, how we are going to basically know for this particular group who is the smallest, because if we know who is the smallest, right, or the value to propagate, right, that is the smallest value you want to propagate to all of to that particular entire components, then I am going to give you. So if you have this value to propagate, so then you can call your DFS to any node of that particular component, and with this value to propagate also as a parameters, and you can standardly run your DFS to basically fan out or propagate to all of its node with this value to propagate. So not basically override, stored it to our DP, stored it to all the node as a key, and for that particular for different keys the value is constant, the value is going to be value to propagate. Now you will definitely ask me, how, Shouvik, you are going to basically know the value to propagate? Then I think the problem is solved. Now tell me only last things, how you can ensure the smallest value is going to propagate when we are making a call to any node of the DFS, any node of that particular components. We make a DFS calls to any node of this particular component. So now actually the tricks that I have applied, you can like follow different approach also, which is in big of n square complexity in kind of like quadratic Go, but I have incorporated exact big of n Go, like exact big of 26, not big of n, exact big of 26, because how many node we have we have at max of only 26 node. Yes, so this count can be, sum should be at max of 26 node we have it in our class. So I am able to do it in exact big of 26 to basically create your DP tables, the mappings from this particular key, that is the mapping. So exactly that we need, right? Otherwise, so we can just iterate to our base strings to basically fetch the value from our DP tables. What is the minimum mapping for this particular key? Then we can just update, we can just store to our answer. So we just need the value to propagate for a particular component, So now I am basically ask you, can you start your DFS from small a to z? Can you start your DFS from small a to z? So what I am asking, you can run a for loop for I in range, whom? Tell me guys, in 26, because we have only 26 node, and if my visited of this particular node, what is the value of this? I can write it character of I plus 97. So that is the characters. I have basically done it because I am I plus 97. I think you guys are already getting, because that is the ASCII of the A. Small a in ASCII is 97. So as I am playing the game from index from 0 to 25, so I am basically making it in the range of 97 to 122 or 123, whatever it is, like small a to small z ASCII, and I am using the CHR of, that is I am getting the characters. Let me just quickly check if I am done the exact same things to our code also. Yes, we are doing the same things in our code also, so we are good. So now I am basically asking you, if that particular things is not visited, if this particular things is not visited, then you can trigger your DFS, you can trigger your helper or the DFS functions to basically consider that is the smallest to basically fan out or propagate to the entire component, So I am basically asking to fan out CHR of I plus 97 and CHR of I plus 97 to fan out or to propagate to all of its neighbors. So how actually my DFS should be looks like? It is going to be very simple. Let me just quickly write the pseudocode. So first one is the value, right? And the second one is the value to tell me guys, value to propagate. So this value to propagate is not going to change internally on recursive functions call of the DFS, right? So what we are doing, we first going to mark visited of this value, because that is our node to be 1. I am going to store my DP of this particular value because that is my key. And what is the value? Value to propagate, because I know for the entire node, entire graph component, I will store the value to be value to propagate only. Now what I can do, very standard DFS for neighbor in whom graph of what is the current is nothing but value. I am going to iterate to all of its neighbor. I am basically going to check if my visited of neighbor, right? Visited of neighbor is equals to 0. Very standard DFS I am writing. Then you can make a call of helper to your neighbor and your value to propagate as it is, because I just want that is the smallest value for which it is not visited, right? So here you can see the beauty. So this things is going to set your DP tables entirely. So how actually going to make sure it? Who is actually going to make sure it? To basically store the smallest value to all of its to the entire subblock. So this for loop is making sure that, because the for loop is iterating from 0 to 26, right? This for loop is iterating from 0 to 26. So when we are, let's suppose we have the component A, P, Q and S. So I am on every go, there is no chance your DFS is going to be triggered from P or Q. A is going to be skipped, and your DFS is going to be start from P, and it's populate P as the smallest to everyone. That is never going to be happen. Never going to be happen. So you will always, as we are running a for loop from 0 to 26, that is the smallest to largest, we are always making sure we start our DFS. We are if there is a subgraph, if there is a subgraph of a particular node, let's suppose here we have a subgraph starting from A, then this for loop is actually making sure by iterating from smaller to higher, when it is going to find anyone which is not visited, then it is start a DFS from here, and it is going to mark every entire graph to be A. Not entire graph, actually update our DP tables per actual key to value map for the entire subgraph. And when maybe and now when you are in these particular things, when you are in P, I guess you guys are already getting, when let's suppose you are in P. So for P, is it visited already? So here you can see. It is never going to true this because we have marked every of them. This is visited, this is visited, this is visited, this is visited, and for all of the visited, key stored, key to value like DP tables updated. So it is already visited. So that is the beauty you have to incorporate to your DFS. So start from 0 to 26, and when you are going to find any of them which is unvisited, then from that particular node propagate, from that particular node fan out, from that particular node propagate the entire smallest characters value to the entire subgraph, and mark every of them to be visited, because for them we have done the calculations with the smallest value to be possible to this particular subgraph. Because there can be possible, right? For B also it is going to be updated, because we don't need, we have already updated with the very smallest value. And who has make sure that this for loop actually making sure by iterating from smaller to higher, So that is basically making sure who is the smallest node. If in a particular subgraph, that node is going to be picked on the very first go of my DFS call, and on the value to propagate call. That is my helper or the DFS calls, and that value is going to propagate to the entire subgraph. That is basically making sure this for loop. So I am repeatedly, that's the reasons I am repeatedly stating, guys. Please take a note on this. That is actually the very important things. How you can optimize your time complexity in big of just 26 to create that DP tables, to create your DP tables like this one. So I think you guys are able to understand. But if you have any doubt on any particular portions of this particular explanations that we did, please do a comments. I will be more than happy to answer this. Now we can quickly discuss the time complexity. Not on the time complexity. Now we can quickly discuss the code iterations part. The code iterations is going to be very straightforward, very straightforward, very template way that we are following to our all the videos in graph playlist. If you are following the exact template we have just written. So only the how you are basically triggering your DFS. So that's actually the things. No guys, your template, whatever I have made, I have already shared to you. Now using that template, are you able to crack to an interview? That is in your hand actually. So if you are not able to make your DFS calls, if you are not able to modify your template according to the question, then actually you need a good amount of practice to tweak your template based on the question requirement. So that you have to, that only one can be able to achieve by rigorous practicing. There is no shortcut on this. I can provide you template, but how to apply, when, what actually you have to change. So that things is going to become only a rigorous practice on. So now we can quickly go to the code iteration. So here you can see graph is default dict of list, n is len of s1. For I in range n, I am creating my graph. Graph is s1 of I dot append s2, graph of s2 dot append s1, because undirected graph, very straightforward. dp is going to be default dict, viz is going to be whom, default dict of int, right? Default dict of int. Visited, because on visited we are storing only 0, 1 only, if it is visited or not. Now here you can see the beauty. Here I think I have written the exact same code for I in range 26, which is basically making sure my DFS is going to be called with the smallest node of that particular subgraph. If that character is not visited, then call your helper to, first one is the value, second one is the value to propagate. First one is the value, second one is the value to propagate. So I have passed the value and value to propagate. I am marking the visited of that particular value to be 1, dp of this value to be value to propagate. Now I am going to call to all of my neighbor for neighboring graph of value. If it is not visited, then recursively make a helper call, and your helper is going to be now on next functions call. Your value is going to be changed to your neighbor, and value to propagate is going to be constant, because that is the smallest value you have to populate, you have to propagate, you have to fan out to that entire subgraph component that you are playing, right? So that is going to be constant to all the functions call of that particular component. And finally, we have created our DP to be ready. Now you can initialize your answer. Now you can iterate to your base strings. For each in base strings, just append answer plus equals to dp of each, because dp of each is already holding the mapping from that particular character. What is the smallest character you can map it? What is the, for that particular character, what is the smallest characters you can map it? You can map it. So you can call your DP and store it to an answer, and finally, a very good step to return it. Very good step to return it. Yes, guys. So that is all about the entire problem explanations and the intuitions building and everything. So we have done like detailed whiteboardings and line by line code iterations and the exact my DFS template that I am going to follow for all of my submissions. I have explained the entire things. Now we can quickly discuss the time complexity, right? So can you guys tell me the time complexity? I think you should be able to tell it. So the time complexity is going to be, so this is kind of a big of 26 only. These things, this entire job, this graph creations is going to be taking off big of in, right? This is going to be taking a big of in. This is big of 26 only, right? You guys are getting it already, right? Because if we are making our helper calls or our DFS calls only if the node is not visited, and when we are making a call to the DFS, then it is basically making the entire subgraph, entire that particular subgraph to be visited. Because so that's the reason every node, how many nodes we have? We have 26 nodes. So all the nodes are visiting only once. So the first big of n for this graph creation. Second big of 26 is to create our DP. So that is the optimizations, guys. Big of 26 only. And next one is big of n to basically build our answer from the base strings. Build our answer from the base strings. That is the time complexity. You can write it in simplified forms in big of n only, right? Big of n only. And on space perspective, on space complexity, can you guys tell me the space complexity? So on space complexity, we are using a space of graph, but it is of kind of big of 26 cross 26 at various case. So we can consider it's constant only. Then we have this DP visited. So you can consider it is of for let's suppose we have key to value for every, so 26 cross 26, that is of graph storage. Then big O of n for DP plus big O of n for our visited. That's it. All about recursion stack trace we can ignore for sure, and answer returning we can consider a big O of n, but that is an optional, because that we anyhow need to return the answer. So it is kind of a big O of how much, 3n plus some 26 cross 26. So I can write it in big O of n only. So that is all about the time complexity and space complexity. If you can see, our submissions is like 94-95% faster than all over the submissions over the Leetcode, and it is bound to be like it is of 3 milliseconds only. Now are they allowing me to check the time complexity? Should be big of n. The server is busy. Very good. Can they allow me to check the space complexity? Yes, space complexity we have predicted very correctly. It is of big of n. We have also wrote it in big of n. On time complexity, is your server is empty? Okay, your server is empty. So it is stating like big of n plus n kind of complexity, because big of v plus e, because we are doing a graph traversals all together to all the node. But big of n plus n, basically this they have considered as big of n, and this base strings they have considered as a big of n, right? These two things only. So base strings length they have considered as m, and S1 S2 length they have considered n only. So we have already considered big of, you can consider this n, and you can consider this n. So then on that case also big of n plus m, what they have basically showed us, but it is on big O complexity, it is of big of n, and it is bound to be the most optimized time and space complexity you can achieve for this particular problem. So yes guys, so these problems I have to say is as simple as that, but from this define a graph, applying the DFS, propagate the smallest value to the entire subgraph. This concept is literally are on crazy level, and you have to identify these things to an interview, and that is going to become. So how you can relate these problems is altogether a graph problem. You have to think about a DFS propagations of the smallest value to the like component graphs, undirected component graphs. So these things actually the interviewer is basically looking for to check it. If you are able to identify this is a graph problems, then the entire intuitions, entire whiteboarding we have done. So please try to explain this way that we are explaining to the in every video that we are making. Try to explain as it is in your interview, then there is no way you are going to be gets rejected. And yes guys, so that's it all about this particular problems. And if you guys are able to understand till this point, I would definitely suggest you please do. I guess you guys are already doing, but please do guys, please do subscribe to our channel, and please share the videos to your friends circle who are also preparing for top product based company and brushing up their DSS skills. And please turn on the notification so that when we are going to live to our next video, you guys are going to get the notification as soon as possible. So that's it guys, that's it for today. Let's meet tomorrow with another video question. Bye guys, bye.